If you have seen yourself working with hypothesis tests or statistical inference in general, you must have actually come across the word z-scores, or you must have seen z-scores. And I'm sure one way or the other you've actually asked yourself, what exactly is a z-score? I've asked myself the same question, even though I've just, sometimes find a way to just run around it and just not want to try to understand it. But I keep coming back and ask myself the same question. What exactly are these things called z-scores, and why do we have z-scores in the whole of anything that has to do with normal distribution? So in this video, I will try as much as possible to explain what a z-score is and why we have them in the first place. But before you understand what a z-score is, actually, you need to understand two key things, and that is the concept of the normal distribution and the standardized normal distribution, aka the standard normal distribution. I think I can use the word. So let's try first and understand what a normal distribution is. In the simplest way I can explain it, a normal distribution is one of the most popular probability distributions out there in data analysis, in statistics, or in machine learning. Okay, it is one of those distributions that is symmetric, and it is a type of a continuous probability distribution, which simply implies that the random variables that makes it up are actually continuous in nature. By continuous, it means these values are measurable, they can take decimal values, and they are not countable. I have a video on basis of continuous distribution and that of continuous variables. I'll be linking those videos probably in the top right corner, and also in the description. You can just check them out after watching this video. So one of the distinct property of the normal distribution is that it is symmetric, and by symmetric it means that if you divide it from the center into two parts, the first half, or the half by the left, can actually mirror the half on the other end, that is the half by the right. Another distinct property of the normal distribution is based on the fact that the mean is equals to the median, which in turns is equals to the mode. Now we need to know that for a random variable x, uppercase x, that is defined by a normal distribution, we have two parameters that defines them. In simple terms, it means that whenever we have a normal distribution in general, that bell curved shape, and that reminds me, the normal distribution is also known as a Gaussian distribution or a bell-shaped distribution, because it has the shape of a bell. So whenever we have a normal distribution, we actually have two variables that defines it, that determines its shape and position, and those two variables are the population mean and the population standard deviation. So that simply implies that the normal distribution is usually used relative to a population data. So a normal distribution can take several values of population mean, and it can take several values of population standard deviation. Now the population mean and the population standard deviation actually affects the shape and height and position of the normal distribution. So let us start with the population mean. Now the population mean of a normal distribution actually affects the center of the distribution, and the population standard deviation affects the spread or the width of the distribution. So let's assume I have a normal distribution that has a population mean of 2.5 and a standard deviation of 1.0. Now you can't compare this type of normal distribution with the one that has a population mean of, let's say, 3.5 and a standard deviation, a population standard deviation of, let's say, 2.0. The one that has a standard deviation of 2.0 is going to be more spread out compared to the one that has a standard deviation of 1.0. And also the distribution of 3.5 is going to be having its center located at 3.5. That means it's going to be moving more towards the right compared to the distribution that has the mean as 2.5. So I think that's kind of give you an idea of what a normal distribution is. Now once you have the value of the population mean and the population standard deviation, you can kind of construct a normal distribution. Now let's go back to the example of mu is equals to 2.5 and the sigma is equals to 1.0. So what does the normal distribution looks like? At the center we have 2.5. Remember that the mean represents the center, so the standard deviation determines the spread of the distribution. So I have 2.5 at the center, then towards the right I will have to have 2.5 plus 1.0, and that gives me 3.5. okay, So that is the first standard deviation towards the right. Then 3.5 plus 1.0, that gives us 4.5. 4.5 plus 1.0, that gives us 5.5. So that means that we have 3 standard deviations towards the right. That is 2.5 at the center, then we have 3.5, we have 4.5, and we have 5.5. So this is the sort of like the area towards the left, towards the right. Okay, so let's move towards the left. So we have 2.5, then we'll subtract 1.0 from 2.5 to go towards the left. So that is 2.5 minus 1.0, so we have 1.5. For the second standard deviations towards the left, we have 1.5 minus 1.0, that is 0.5. And then we'll do the last one, that is 0.5 minus 1.0, that is minus 0.5. So we have 2.5 at the center, and towards the right we have several values, and towards the left we have several values. Each of the values 3.5, 4.5, 5.5, or 1.5, 0.5 minus 0.5 are called the raw scores of a normal distribution. So we use letter x in lowercase to represent them rather. So mu is equals to 0.25, mu is equals to 2.5, sigma is equals to 1.0, and we have I think 6x scores right here. Yes, we have x 3.5, x 4.5, x 5.5. We also have x 1.5, 0.5, and minus 0.5. And this is the basis of a normal distribution. Like I said earlier on, when you decide to change the values of the mean and the standard deviation of a normal distribution, it affects the shape. So if you increase the value of the population standard deviation of a normal distribution, it begins to spread out. Okay, and as it spread out, it increases in width, hence it decreases the peak, that is the height of the distribution. And if you decrease the standard deviation of the distribution, it begins to like shrink, like it begins to get smaller in width. And as it gets smaller in width, the height of the distribution actually begins to change. Okay, so this is kind of related to the concept of kurtosis in exploratory data analysis. All right, so that being said, you can also decide to change the value of the mean. And if you change the value of the mean, it moves the distribution from one point to another. So if you change the value of the mean from, let's say, 2.5 to like 3.5, it will move it from the center point of 2.5 and move it to the center point of 3.5. You can actually visualize this thing. Okay, all I've said about the shape when you change the value of mu and sigma by using a Desmos calculator. I would have done that already, so I'll be linking a Desmos calculator right here so you can just play around it. Now remember that a normal distribution is a probabilistic distribution, so that means I can start asking questions relative to probability, like, okay, so if the mu is equals to 2.5 and the sigma is equals to 1.0, so what is the chance that a random variable is going to be greater than, let's say, 5.5, or a random variable is going to be between 0.5 and 4.5. You know, questions like this needs to be asked whenever we find ourselves working with a normal distribution. Now, this is where it gets interesting. From the mathematical standpoint, whenever you have a normal distribution and you're trying to get probabilistic value between two raw scores of that normal distribution, the formula is the integral. Then we have the limit of b and a, and we have the f of x dot dx. Okay, so now the f of x right here represents the probability density function that defines the normal distribution. The b in this case of ours represents the upper limit, which is a 4.5, and the a represents the lower limit, which is actually 0.5. So that means for us to get the area bounded between 0.5 and 4.5, we are going to like take the integral between 4.5 and 0.5, then we have a probability density function. Now this is where it gets interesting. The probability density function that defines a normal distribution is given as this. As you can see, this is quite mouthful. You know, it has a lot of, you know, complicated, not really complicated, but just one or two details. And mathematicians and statisticians realize that these you know, getting the integral of this function is kind of like tedious and will require high level of mathematics. So as smart people as they are, they try to play around numbers, okay, and be like, okay, let's look for a sweet spot for the value of the population mean and the value of the population standard deviation, in the sense that once we do that, instead of going through the stress of integrating this density function, okay, we can just have a standard value or a standardized value that can make things easier for us. So we won't have to go through the stress of integrating such a complex function. We want to get the probabilistic value between two random variables under a normal distribution. I hope that makes sense. So after a lot of research and stuff back then, in the 80s and 90s, they were able to find the fact that once the population mean of the normal distribution is equals to 0 and the standard deviation is equals to 1, then some values will actually sort of cancel out and water down the distribution into something easier. And in fact, we won't be having the raw scores x again. We would now be having what we call the z-scores. So the distribution that comes as a result of us having a population mean to be equals to 0 and the population standard deviation to be equals to 1 is what we call a standard normal distribution. So this is how we move from a normal distribution to a standardized normal distribution. So once again, for a normal distribution, you can take several values of mu and you can take several values of sigma, and the shape can vary based on the value of mu and sigma. But for a standard normal distribution, it means that we have just a single value of population mean and we have a single value of population standard deviation and we have just one shape. So for a standard distribution, our mu is equals to 0. That is the center, and our sigma is equals to 1. So obviously, towards the right, we'll be having 0 plus 1, that is 1. 1 plus 1, that is 2. 2 plus 1, that is 3. Down towards the right, 4, 5, 6, 7. And towards the left, we have 0 minus 1, that is minus 1. 0 minus 2, that is minus 2. 0 minus 3, and that is minus 3, minus 1, minus 5. So the values of 1, 2, 3, 4, 5, 6 towards the right, minus 1, minus 2, minus 3, minus 1, minus 5 towards the left are actually known as z-scores. So this simply implies that if I have a normal distribution of mu is equals to 2.5 and my sigma is equals to 1, I can standardize that distribution into a standard normal distribution for it to have a mu that is equals to 0 and a sigma that is equals to 1. So that means values like 3.5, 4.5, 5.5 will have their corresponding z-scores of 1, 2, 3, and values like values like 1.5, 0.5, and minus 0.5 will have the corresponding z-scores of minus 1, minus 2, and minus 3. So the question is, how do you convert the raw scores x of a normal distribution into a standardized z-scores z of a standard normal distribution? And that is where the formula comes in. And now the formula is z, which is the standard z-scores, is equals to x minus mu divided by sigma. So where x in this case represents each of the raw scores, and mu represents the population mean, and sigma represents the value of the population standard deviation. So let's go back to our normal distribution of mu is equals to 2.5 and our sigma is equals to 1. So let's say I'm interested in the probability that x is let's say less than or equals to let's say 1.5. Okay, so probability that x is lesser than or equals to 1.5. Obviously, to get this value, we can see that we are moving from 1.5 towards the left, so that means this area has actually been swept. Now for us to get this value, we need to standardize the value of the raw score, and to do that, we are going to be saying z is equals to x minus mu divided by sigma. So our x in this case of ours is actually equals to 1.5, our mu is equals to 2.5, and our sigma is actually equals to 1. So that means 1.5 minus 2.5 divided by 1, and that's going to be equals to minus 1 divided by 1, which is equals to 1. So that means our z-score in this case of ours is equals to 1. So that simply implies that probability that x is lesser than or equals to 1.5 is equals to probability that z-score is lesser than or equals to minus 1. We've standardized the raw score into a z-score. Then we can now get the area under the z-score, okay, towards the left. Now the good part is that when it comes to getting area under the z-scores, we have standard normal distribution tables that are actually available everywhere. All you have to do is to just try to locate the value on the vertical axis and on the horizontal axis, and the table is going to get you the area under a specific z-score. And there are also calculators that can actually help you to do this. In fact, most of these softwares like Stata, Excel, SPSS, and they can actually help you calculate the area under the z-score. But in the crude method, we actually use statistical tables. I'm talking about the standard normal distribution table right here. So, and this is how you can actually work with the z-score and use the z-score to get the area under the curve. So I hope I have been able to explain how z-scores came about and how you can actually use them to get the area under the distribution. Don't forget the fact that the total area under a normal distribution and even a standard normal distribution is equals to 100% or 1. So you should actually pay attention to that. So that simply means if you have questions like let's say so let's say we have our mu is equals to 2.5 and we have our sigma to be equals to 1, and you're interested in the area between let's say something around 0.5 and 4.5. So right now you've kind of divided your area into the whole distribution rather into 3 areas. So we have the area in the middle, which is the largest area, the area we are interested in, the shaded area. Then we have a little bit of area towards the left and we have a little bit of area towards the right. But something you have to notice that the area of A, which is towards the left, and the middle area, which is B, and the area towards the right rather, which is C, all of them must sum up to give you 100% or will give you 1. So that means to get the value of B, which is the area in the middle, so that will be the area towards the left, okay, plus the area towards the right. Then you sum them up, then you do 1 minus the sum of the area towards the left and the area towards the right. So I think that makes sense, and I've made it as easy as possible. So this is how you use the concept of z-scores, and the application is very, very wide. We use it in IQ scores, we use it in education in general, we use it in psychology, and like I said in my last video, okay, the normal distribution, the normal random variables are actually occurring in real life situations, in biological variables. So you will find yourself using z-score if you are in the biological field, and also it's applicable in the finance field. So you can actually find yourself using this. If you enjoyed this video and you learned something new from this video, please don't hesitate to give this video a thumbs up, and also subscribe to this YouTube channel. Do you feel I missed something or you have some questions for me? Please don't hesitate to go down to the comment section and drop your questions. I would be willing and be ready to answer all of them. Thanks for making it to the end of this video, and if you want to learn the needed statistics for your data analysis journey, I actually have a playlist for you, which I'll be linking, I think right here or right here. You can check that playlist out, and if you are a newbie and you want to become a data analyst, I have the perfect introduction video for you that will actually make it easy for you to start understanding the concept of data analysis. I have a video right here for you. Thanks for making it to the end of this video, and we'll see you in the next one. Bye for now.